I've got one more multi-step example for you. And then after that, really, they're all the same. You just got to pick them apart, find the relevant information, and use your energy diagram. So here we go. A 35.2 gram piece of ice at negative 50 degrees Celsius is heated until the resulting water, interesting, water is at 30 degrees Celsius. Calculate the energy absorbed. Absorbed tells us this is going to be an endothermic process, in case you couldn't tell by the fact that it's going from ice to water. And even though I haven't solved this problem yet, I have no idea what the answer is going to be. I very intentionally picked this kind of setup because there's a couple of interesting things that we're going to run into. But first, let's answer the main questions. The where are we going, how are we going to get there, how many steps do we need to go through, etc. So the mass isn't super important to me right now. I'll pull that in later. I'm starting at negative 50 degrees Celsius, and I'm going to end at 30 degrees Celsius. So let's see where that lands on our energy diagram. And again, I don't have the exact numbers on here, but that's fine. I'm just looking for relative positioning. So if I'm starting at negative 50 degrees Celsius, that's going to be down here-ish. Okay, that puts me pretty, I was going to say solidly into solid territory, but that's just bad. Point is, we're down here. We are in the solid area. And we're going to end at 30 degrees Celsius, so here-ish. Okay? Not super far to travel, but there are 3 different processes that I need to go through to make this happen. Okay, I need to heat up my solid to 0 degrees Celsius, and then I can melt that solid until it is a liquid, and then I can heat up that liquid until it hits 30 degrees Celsius. So 3 different processes, which means 3 different equations. Q equals m delta TCS, and Q equals m delta H of fusion, and Q equals m delta TCl. I'm going to solve each of those 3 equations, and I'm going to add those 3 answers together, and that will be my final answer for this entire problem. Okay, so Q equals m delta TCS, delta H of fusion, delta TCl. So let's do that. Okay, so my Q total, it's going to get a little squishy here, is going to be the sum of 3 problems. An m delta TCS with an m delta H of fusion, and then finally m delta TCl. Okay, so let's tackle these one portion at a time. Okay, let's double check our melting points and boiling points, make sure that we're aware of those. So water melts at 0 degrees Celsius. This is really, really important because what a lot of people want to do when they see delta T, and I realize I'm jumping ahead of myself, when they see delta T, they just want to take these 2 numbers and fly with them. Don't do that. You have to think about where each stage is beginning and ending. So let's start with this guy right here. Our mass is 35.2 grams. That's what it's going to be the entire time. Now, delta T. Our initial temperature is negative 50 degrees Celsius. For this stage, our final temperature is not 30 degrees Celsius. Our final temperature for delta TCS is 0 degrees Celsius. So that's one of the reasons I want to do a problem like this, so that you can see that this process ends at 0 degrees Celsius. So my final temperature for this step right here is going to be 0 degrees Celsius, and then careful, it's final minus initial, so minus negative 50 degrees Celsius. Okay, so that looks a little bit gnarly, but that's fine. And then our CS is 2.06 joules per gram degree Celsius. 2.06 joules all over grams degrees Celsius. Okay, so I'm gonna simplify this a little bit. So we've got 35.2 grams times 0 minus negative 50 is going to be just 50. Again, remember this number here didn't have sig figs. Times 2.06 joules over grams degrees Celsius. Okay, so there's my m delta TCS portion. So this came down here and became that. I just know this is going to get a little messy, so I want it to be pretty. There, I said it. I meant pretty. Okay, so there's that. Let's do this delta H fusion portion next, and I'm just going to kind of do it down here. So our mass is still 35.2, 0.2 grams. Okay, and then I need delta H fusion, which for water is 334 joules per gram. Remember, we're not always going to do this for water. This is specifically for water. If it's for something else like ethanol or acetic acid, these numbers will change, and these numbers will all change. But the constants, the equations, everything else, that will be the same. When you use them, will be the same. Okay, so we're going to use delta H fusion, which again is 334 joules per gram for water. So 334 joules per gram. Okay, no need to simplify that one. I'm just going to rewrite it down here. So 35.2 grams times 334 joules per gram. Okay, there's my step 2. This is my step 2. This was step 1. All right, last bit. I have warmed up my solid. I have melted my solid. Now I am going to heat up my liquid. So 35.2, still my mass. Remember, this is all physical change. All right? Even if it was a chemical change, the mass would still be the same. That was not an intelligent thing to say. All right, here's delta T. Again, don't just take these two numbers and do fun things with them. You have to think about where is this stage starting and ending. So this blue portion starts at 0 degrees Celsius. That's my initial temperature. My final temperature will be the 30 degrees Celsius. So 30.0 degrees Celsius, that's where my sig figs are going to come from, minus 0 degrees Celsius. And then delta T CL, CL for water is 4.18 joules per gram degree Celsius. 4.18 joules per gram degree Celsius. Okay, so this will simplify. This is my step 3. I'm going to rewrite it down here and solve for delta T in there. So still 35.2 grams. And obviously you don't need to do this whole rewriting thing. It's just making it a little bit clearer visually. So I thought that might be good for what we're doing here. So this is just going to be 30 degrees Celsius. And then 4.18 joules per grams degrees Celsius. Okay. So let's check all of our units. Grams cancel all the way across the board. Degrees Celsius cancel in this step and in this step. There's no degrees Celsius to cancel here because this was my phase change. It's not a temperature change. And that leaves me with joules in this step, joules in step 2, joules in step 3. Joules plus joules is just going to be, lo and behold, joules. Okay, so I'm going to solve each of these individually. So I can do the multiplying and dividing sig fig rule, and then I'll add them together for that rule. So what, 35.2 times 50 times 2.06, I get 3 sig figs, is going to be 3630 joules plus, and here's my step 2, 35.2 times 334. 3 sig figs again. Looks like 11,800 joules. And my step 3, 35.2, of course, times 30 degrees times, except the 30 is gone, or the degrees is gone, 4.18. And to heat up that water, that will be 4,000 19,410 joules. Okay. When I add these all together, this is significant in the tens, so is this one, but this one's only significant in the hundreds place. So I'm going to keep the hundreds place when I add these three values. So 3,630 plus 118,000, 11,800 plus 4,410. Rounded to the hundreds place will be 19,800 joules, or 19.8 kilojoules. There we go. There's your Q total for that 3-step problem.